Okay, when dealing with chemical kinetics, remember it's all about how fast or slow the reaction goes. We're going to take this little reaction that we have right here, just a pretend reaction. A turns into B, meaning that A represents the reactants, B represents the products. So A turns into B. That's the basic reaction here. And we're going to represent these two letters visually with these two sets of colors. This is a larger picture right here, where the red balls represents A, and the blue balls, yes, the blue balls represent B. So notice at time 0, which means before this reaction even took place, we have 100% A. It's all red. Then once the time starts and we start going in the forward direction of this reaction, we're starting to produce B, we're starting to produce blue. 20 minutes later, we might have 40% red and 60% blue. 40 minutes later, we might have 20% red and 80% blue. Notice at time 0, we started with 100% red and 0% blue. So as time goes on, we produce more B, more blue, and notice that the amount of A is also decreasing. B is increasing. So we can track this, we can find out a rate. The average rate of the reaction is equal to the change in concentration of B divided by the change in time. Here I have 0B. I could actually go into this picture right here and count every single blue molecule, and that would be a change from 0 to, let's say, 20. If I divide that by my time, then that's my average rate for the change in the moles of B. This little symbol right here is delta, which stands for the change in. Change in the moles, or change in the number of B, divided by the change in time, which is 20. I could do the same thing with the red. I could take my number of red balls here and subtract the number of red balls here, and that would represent the change in the red balls, the change in the number of red balls. Divide that by my change in time as well, and it would also give me the average rate. However, notice that right here there's a negative symbol for the change in A. Over here there's no negative symbol for the change in B. That's because A is disappearing, B is appearing. So the appearance is a positive thing, and the disappearance is represented with the negative symbol. Okay, you would actually notice that the rate of disappearance of A is actually equal to the rate of appearance of B. So the rate of disappearance is equal to the rate of appearance. That's not always true, but notice that we have a 1-to-1 ratio up here. So the coefficients here dictate the rate of appearance versus the rate of disappearance. If there was a 2 right here in front of B, then that would mean that B appears twice as fast as A disappears. And vice versa. If there was a 2 right here and nothing right here, or a 1 implied right there, that would mean that A disappears twice as fast as B appears. Okay. So now let's not use imaginary scenarios. Let's use actual chemicals. I want you to look down to midway down your page, and we're looking at this reaction right here. This is butyl chloride plus water produces butanol and hydrochloric acid. Now notice we're still doing a 1-to-1-to-1-to-1 ratio, so therefore the rate of appearance for my products is going to equal the rate of disappearance for my reactants. And therefore I can monitor this by picking any one of these compounds and noticing the change in it versus the time. So if we look at this data table right here, Here's our time. Here's our concentration. This little symbol right here means concentration in molarity. And then this stands for average rate, which is my molarity divided by my time. So molarities per second. Okay, so at time 0, I start with 0.1 molarity butyl chloride right here. That would be 100%. Okay, then as the reaction starts and the time goes down, notice that my molarity, my concentration, my amount of butyl chloride goes down. Why? It's disappearing. Okay? So this change in butyl chloride would have a negative value in front of it because it is disappearing. Okay? After 10,000 seconds, there is 0 molar butyl chloride left. So what you're going to need to do right now is down here on this graph, what I want you to do is I want you to plot all of your time points with all of your concentration of butyl chloride. Okay? Concentration of butyl chloride will go on the y-axis. Time, which is always the independent value, will go on the x-axis. Okay? So for example, at time 0, which is right here, the concentration of butyl chloride is 0.1, so you would make a dot right there. Go ahead and put all the rest of the dots on there, and then when you're done, you should have a nice, smooth curve. Okay, so tomorrow when you come into class, I want this graph right here to be completed. You should have your points, your dots representing the concentration of butyl chloride versus time. Go ahead and draw your nice smooth curve, and then we'll do this part right here in class together. If you feel up to it, you should have enough information from what we've talked about in this video to go ahead and try to answer this question right here. It says, using the data from table 14.2, calculate the average rate of disappearance of butyl chloride over the time interval from 50 to 150 seconds. This right here tells you how to solve for average rate, and the question says calculate the average rate. So you should have enough information to solve for this question. So I want you to come into class with this finished and an attempted answer at this question right here.